So okay. So we'll continue on from our discussions this morning. I know it's late in the day, first day back for everybody, so I'll try to get things active as soon as possible. That extra problem sheet I handed out to you this morning, we're soon going to be working through some of the problems on that. Okay, we're going to keep ourselves active. So where were we this morning? We met the definition of the partial derivative of, for the moment, of a function of just two variables. The definition was like this equation appearing in 1.4 here on page 2. This is showing the partial derivative of a function, two variables, with respect to its second variable. If you're using the term y to indicate the second variable, you would call this the partial derivative of f with respect to y. Okay. Just like the one variable case, it's a limit of the relative change in value, the change in value of the function, when evaluating it at a base point, here written as xy, and a nearby point, but here the nearby point is produced by just a small variation in the y coordinate. We're doing a partial derivative with respect to y. The x coordinate is unchanged. It's the relative change in value. It's the change in value. If that was just the numerator, it'd just be the change in value, but it's relative to the amount of change you've made in the argument, okay? And that's important, okay, because if you move a long way away from the base point, you might see a large change in value, even from a slowly changing function, because you've moved a long way away from the initial point. So if you're going to judge the size of the, if you're going to judge the change in value of the function, you need to judge it relative to the distance you've moved away from the initial base point, so to speak. Okay? So we have the change in value of the function f relative to the size of the change in the variable, and we're taking the limit of this as the change in y goes to 0. And this produces the partial derivative of f with respect to y. We ended last time by working through this example 1.1, where we took a particular function x squared y, and we applied the definition of the derivative, and we found that its derivative with respect to x is 2 times xy. And we might also do another quick version of the example, which is suggested to you here, is to work out the y derivative of that function. So this, if you like, is the second half of example 1.1. So our function f of xy is x squared y. And this time we're going to show that df dy is x squared. Maybe yourselves just take a minute. I'll just blank this, just freeze the screen as I'm writing it out. We'll write out a similar proof for this using the definition of the derivative, similar to what we did this morning for the first part of example 1.1, and that's reproduced in your notes on page 2. Okay. Well, I'll unblank, the definition of what we're doing is, well, I'm just going to repeat the definition here. It's always a good place to start. So the derivative with respect to y is to look at the change in value of the function f when you change the second argument from an initial value y to a new value y plus delta y. But delta y is just a two-letter name for the change in value of the y coordinate. You're looking at that change in value relative to delta y. So apply the definition of the function there. F of xy is x squared times y. Apply that there and see if you can get out the required result, that df dy is equal to x squared. Okay. Work together with your neighbor by all means. Help them out. Get confirmation from them. They're doing the right thing. Don't dawdle, this is a short exercise, relatively straightforward. If you follow the treatment we gave to the x derivative, so you're at this stage, introduce the definition of the function f. When f is presented with two arguments, it squares the first one and multiplies the result by the second argument. Okay? So you can apply that here. You're going to square x, multiply it by the second argument there. This thing will just be x squared y. Shall we reveal? Okay, so here's what the calculation looks like. So this is just the definition. The next step is to bring in the definition of the function f. So f squares its first argument and multiplies the result by the second argument. So we have x squared multiplied by y plus delta y here for the first term, and subtracting x squared y from the second term. And that's all over delta y. We have to take the limit of this as delta y approaches 0. Okay, it's not a trivial limit to do because you've got delta y in the numerator and the denominator. And if the bit that's converging to 0 is in the denominator, that's potentially problematic because it's going to get smaller and smaller and smaller, and that might make the whole thing blow up in value, and it might not have a limit. But there is some development in the numerator to do. You can simply multiply out this bracket, get x squared y plus x squared delta y. But then you see that, well, actually, we don't really have x squared y up here because it's subtracted immediately. Okay, so those cancel, and really the numerator simplifies quite a bit to x squared delta y divided by delta. So really, the delta y isn't really there, okay? Because it's in the numerator and the denominator of the fraction, so you can just simply cancel it out. There's no division by 0 problem when you're manipulating this because we're taking the limit as delta y approaches 0. So in the limiting process, delta y is never actually equal to 0. It's getting smaller and smaller for sure, but it is always non-zero, so you can always divide above and below the line by this non-zero quantity delta y. Okay? And that will reduce the limit to just the limit as delta y approaches 0 of x squared. Yeah. But x squared is just happily sitting there, taking whatever value it is, and it doesn't care what delta y is doing, so it's a totally independent variable. So the limit as delta y approaches 0 of x squared will just be x squared. Okay? Because x squared has no dependence on delta y. And we get the claimed value of x squared for the derivative of this function. Okay? But okay, are there any questions or clarification I could give you on any of those steps? Lay down the definition at first of the derivative, then bring in the definition of the function, and then just treat the limit, so to speak, by doing some, pretty, sensible things, simplifying the numerator, getting rid of the problem in the denominator, and so to speak, and we end up with quite a nice limit. Now, what you might notice from that example, both this one and the previous one, where we worked out the x derivative, is we kind of expected those values. We kind of expected those values to come out. So we proved last time that the derivative of this function with respect to x was 2xy. And we're familiar, of course, that the derivative of x squared in the one variable sense, the derivative of x squared is 2x. And that's exactly what you're seeing here. We're differentiating this with respect to x. We're kind of temporarily ignoring, in a sense we'll make precise soon, but we're kind of ignoring in a way y, and we're just differentiating the x part, and we get 2xy. When you look at the y derivative of x squared y, all we see is something times y. In a way, because we're differentiating with respect to y down here, we're kind of ignoring the x, and all we see is something times y. And we're familiar already in the one variable case that the derivative of, say, a constant times y, the derivative of 5 times y with respect to y would just be 5. The derivative of a fixed number multiplied by y, differentiating that with respect to y, would just be whatever the fixed number is. That's exactly what we're seeing there. So this leads us to this, and it's written in bold here, this principle of partial differentiation that we're going to be using. Okay? Throughout this course and throughout your mathematical studies, you'll be evaluating or working out various partial derivatives, but you'll seldom be going back to this original definition. Sometimes you will when you want to prove properties of differentiation or look at something in great detail. But in a practical case, when encountering functions, when encountering standard functions, functions that are made up from or assembled from standard functions, if you need to obtain partial derivatives of those, in practice we're going to use this principle here, highlighted in this bold paragraph. Okay, so this is important. So when differentiating a multivariable function f with respect to one of its variables, say x, what we do is we treat the other variables that the function depends on, we treat the other independent variables as if they were constants for the purposes of obtaining the derivative. We treat the other variables as constants. So really, suddenly, what was a multivariable function now really just becomes a function of a single variable. A bunch of constants mixed in with the variable of interest for the moment, which we're calling x. And then to work out the partial derivative of that function with respect to x, you just simply use the same single variable techniques that you're familiar with for differentiating a function of this one variable x. This would be the linearity of differentiation, things like the product rule, the chain rule, the quotient rule, implicit differentiation, all this family of calculus tools you have from first year. Use those to work out the derivative, all the while treating the other variables that are there as if they were just constants and just carry their values through. If you apply that principle to these two examples that we just worked out, you see you get the same answer. What is the derivative of x squared y with respect to x? Well, you look at it, here's our variable of interest x. We treat the other variable y as if it were a constant. So what's the derivative of x squared times a constant? Well, it's just that very same constant multiplied by the derivative of x squared, which we know to be 2x. So the derivative is just that constant y multiplied by 2x. So 2xy. And its derivative with respect to y, what's the derivative of x squared y with respect to y? Well, when you look at that, we're focusing on the variable y, what you see is this constant, x squared, multiplied by y. So its derivative is just the value of that constant, which here is x squared. The derivative with respect to y, x squared times y, is simply x squared. So with this principle in mind, we can suddenly tackle, more or less, tons of, more or less any nice function which is composed in a standard way using addition or multiplication or composition, composed out of standard ingredient functions that we know the derivatives of. Okay. So for instance, here's a much more complicated two-variable function. In this second example, 1.2, f of xy is x squared times y cubed times the tangent of 2x. So what might its partial derivatives be? Well, let's focus on the y derivative. That's the simpler one to begin with, because this function, with respect to y, this function isn't so bad. Okay. Treating the other variables as constants, what we see here is just some constant multiplied by y cubed. Okay. If we're treating x as a constant, x squared is just some constant value, tangent of 2 times x, just some constant value. Focusing on the y variable, what we see is just some constant multiplied by y cubed. And we know already from our single variable knowledge that the derivative of y cubed is 3y squared, and whatever constant was multiplying the y cubed there is still there multiplying this result now, 3y squared. Okay. So we know straight away now that the derivative with respect to y at this f is 3x squared y squared times the tangent of 2x. The x derivative is a little bit more involved because the structure of the function is a bit more complicated in terms of x. Okay. If we're focusing on the variable x, we see this constant, if you like, y cubed, but we see one function of x, x squared, multiplied by another function of x, tangent of 2x. Okay, so it's a bit more involved. Okay. And to work out that derivative with respect to x, you'd have to employ the product rule. Okay, because you see one function of x, namely x squared, multiplied by another function of x, namely the tangent of 2x. Okay. So what's the derivative here? Well, the y cubed will be present everywhere because it's the constant multiplying this thing. So you need to apply the product rule. So the product rule, remember, you've got, say, this u times v, if you like. So the u is x squared, the v is tangent of 2x. Then over here, we've got the derivative du dx. Here we've got the derivative du dx multiplied by the function v. And over here, we've got u on its own, and that's multiplied by, well, this 2 at the start is part of it, but that's dv dx. And what we're making use of here is dvz, the tangent of z. The derivative of the tangent function is sec squared of z. Sec squared being 1 over cos. So that's 1 over the cos squared of z. So the derivative of v with respect to x is sec squared of 2x, but then, of course, you got another constant 2 there. So actually you have to employ the chain rule. Just take the derivative of tangent of 2x. The derivative of the tangent function is sec squared of the same argument, but continuing to apply the chain rule there, so you've got this inner function 2x. Its derivative with respect to x is 2. So that explains this extra 2 popping up at the front. Okay? So the derivative of v dv dx is 2 times sec squared of 2x. So that's an example of applying this principle of partial differentiation. Okay? And it's that you're going to be applying all the time in this. Okay, so just a few quick things to look at before we get stuck into some more problems. Just looking over the page here, page 3, just talks a little bit about notation. So we're using this curly d or alternative form of d to indicate partial derivatives. You should all employ that notation. There's an alternative notation where if you've got your function f, we might just add a subscript to f. Just add a subscript of the variable name. So f subscript x would indicate the derivative of f with respect to x, and f subscript y would indicate the derivative of f with respect to y. So you might write the derivative of f with respect to x evaluated at a point a, b. You could write that like that. From time to time, you'll see both forms of the notation being used. Skip over 1.3 for now, but I'll come back to it shortly. We can also speak, and we will be speaking a lot more in this course, about higher order partial derivatives. So by higher order partial derivatives, we mean taking derivatives of derivatives. So a function of two variables, f here, and we're still sticking with the two variable case. Okay, we've already seen how a function of two variables, f of x, y, has two first order partial derivatives, df dx and df dy. It has a total of 4 second order partial derivatives. So a second order partial derivative is where you've taken a partial derivative of a partial derivative. Because there's two variables available, there are 4 different ways to do that. You can either differentiate with respect to x both times. That's one of the 4. Differentiate with respect to y both times. The second of the 4. Or you can do a mixed, what's called a mixed second order partial derivative. Differentiate once with respect to x and then with respect to y. And at least at the outset, a potentially different result might come about from differentiating first with respect to y and then with respect to x. Because you could do the derivatives in different orders. Okay? So on the left-hand side of these equations is how we notate second-order partial derivatives, and their meanings are shown on the right. So you would read this as d squared f dx squared for the second-order partial derivative of f with respect to x both times. So it's d dx of df dx. Similar, d2f dy squared is d dy of df dy. And then you've got the two mixed second order ones. Now these are red. These are, okay, the order in which the variables fall in the denominator here indicate the order, but we use it like composition of functions. So the first differential operator that applies is the rightmost one. So this second order partial derivative means taking the x derivative of the y derivative. And if the variables are reversed here, it means taking the y derivative of the x derivative. And this can generalize to third order partial derivatives, fourth order partial derivatives, and so on. We normally only encounter first and second order partial derivatives most of the time. But if you were to encounter something like this, d3f dx dy squared, this would indicate a third order partial derivative because there's 3 variables here in the denominator, the 3 up here. And this would be, you see, reading the variables, it's the rightmost one that's applied first. So those are 2 y derivatives and then an x derivative. So we're taking the x derivative of the second order partial derivative with respect to y. There's a worked example here. We'll move on from it shortly because I'm going to concentrate on the examples on the extra problem handout. But this function we treated in the last example, x squared y cubed tangent to 2x, these are its 4 second order partial derivatives. Okay. The second order partial derivative with respect to y is the easiest one to get because the function is a simple structure with respect to y. It's just something depending on x times y cubed. So if you differentiate that twice with respect to y cubed, you just get 6y. Differentiated once, you get 3y squared. Differentiate a second time, you get 2 times 3y squared, 3y, so 6y. And you still have the other stuff, the x squared and the tangent of 2x appearing, because they're just treated as constants. The second order x derivative is a little bit involved because you're going to have to use the chain rule, and you're going to have to use the product rule twice in combination with the chain rule. So you get a few different terms generated. We'll step through all the details of that. And then you've got the two mixed second order partial derivatives. What we notice here is something very significant. The 2 mixed second order partial derivatives actually come out to be the same function, the same thing. In both cases, 6xy squared times the sum of tangent 2x and x squared 2x. Okay, that's not a coincidence. For most well-behaved functions of two variables, and this generalizes to other cases, the mixed higher order partial derivatives always come out to be the same. All it depends on is the number of each of the variables that there are. Okay? So for instance, and this is called Clairaut's theorem, so for mixed second order partial derivatives of a two variable function, the two mixed second order partial derivatives are the same thing. Okay? It's not immediately obvious from the definition because they do refer to different processes. First differentiate with respect to y, then of x. The other one is first with respect to x, then with respect to y. So it's potentially different, but providing these conditions hold, providing all the second order partial derivatives of f, providing they do exist and are nice continuous functions, then the two mixed second order partial derivatives are going to be the same. We won't be dealing with the proof for that. The proof for that is to do a real analysis. But just kind of understand that this is going to be true most of the time. It would only fail to be true in exceptional circumstances. In the case of badly behaved functions. Functions which are not smooth. Functions where some of its derivatives are not continuous. Okay? But most of the time we shall not encounter these functions. Now this principle of carrying out partial derivatives, you see here, okay, although the only examples we've been looking at have been functions of two variables, there's nothing in this principle here that refers to the number of variables. Because it just talks about the variable that you're focusing on, the variable that you're differentiating with respect to, and the other variables. So equally well, this principle applies to functions of more than two variables. So we just make the point that we can handle those kind of functions in a very similar way. So if you look at example 1.4 here, this function g of x, y, z, it's a polynomial function, x squared times y to the power of 4 times z cubed. It has three first order partial derivatives. Okay? dg dx, dg dy, and dg dz. And each of them we can obtain using that principle of partial differentiation. So what do we get? Well, to differentiate with respect to x, we treat the other variables as if they were constants and differentiate the x part and just use the principles of one variable function. So this is going to be 2x y to the 4z cubed. To differentiate it with respect to y, you just differentiate the y part, keep the other parts the same. To differentiate with respect to z, you treat the other variables, namely the x and the y, as if at the moment they are just constants. Squared times some number to the power of 4. So some number times z cubed. The derivative of z cubed with respect to z is 3z squared, and that other constant multiplier is still there. So when you've got variables multiplied together, the other variables still survive in the partial derivative, so to speak. Of course, if we were to change this, I could augment this by, say, adding in a y squared here. How would these partial derivatives change if I suddenly had a plus y squared there? Will they all change? Would one of them change? Just the y one. See, the principle for working out the x derivative is you treat the other variables as if they're constants. So the first term differentiates as it did. Then you got the y squared. What's the derivative of y squared with respect to x? Well, you're differentiating with respect to x. So the y is just treated as a constant. So all you're seeing here is just some constant. It's a fixed number for the purposes of differentiating with respect to x. So its derivative with respect to x is 0. So that y squared doesn't survive into the x derivative. And for similar reasons, it doesn't survive into the z derivative. It will survive into the y derivative, because y squared is not a constant when y is changing, because it depends on that. We do get an extra term generated here of 2 times y, the derivative of y squared with respect to y. Yeah. So sometimes people make mistakes with that or so on. So if other variables multiply the variable in question that you're differentiating with respect to, then those other variables will survive in the derivative, so to speak. But when they're just out on their own, not multiplying the variable of interest, then those parts won't survive into the partial derivatives, of course. Okay. Now I did skip past something there, the graphical interpretation, which we'd like to just return to. Now there's just a little bit written here. There's a pretty terse description written here, but I've got a bit of an interactive widget to show you, which illustrates the situation. Okay, so when you click through on Moodle, you'll see the lecture from this morning. And just in the description to the videos, I put the scans of the lecture pages. It's already there. You can see what we produced this morning. So this is what a quick diagram we wrote down this morning, which was the graphical interpretation of the derivative of a single variable function. Okay. The object associated to the function f, if f is a function of a single variable x, is the graph of the function f. So you've got the x-axis here. The function supplies height values over points in the x-axis. You get the graph of the function. And the derivative of f is the slope of the tangent line to the graph of the function at that point. This is the line which only crosses the function once in a local neighborhood of that point, and has the same instantaneous behavior, same instantaneous rate of change as the function has at that point. What we'd like to do is supply a similar way of thinking about partial derivatives, a similar graphical interpretation. This is what we can see in this widget here. I'll share this widget on the Moodle page so you can go into it and experiment with it. It's an interactive demo. The code for producing the thing is here, and you can kind of figure out what the various bits of the code are doing. But we're just going to look at the pictures for now. So what we're going to see is we've got a function of 2 variables programmed in here, which is sine of x times y. So the function f is defined as sine of x times y. And what we're going to see here is the 2 partial derivatives of the function evaluated at a certain base point AB. And what we're looking at them is how they look and how they relate to the graph of the function. Now, for a function of 2 variables, what we mean by the graph of the function is actually a surface. Okay? So what you're seeing here in this picture is you've got the x and y plane here. So you've got an x-axis here and a y-axis here, and they define the ground plane. Then the function f of xy gives you height values, which are heights over certain base points with coordinates x and y. When you put all that together, what the function sine of x times y produces is it produces a height for every base point xy. And because sine is a continuous function and multiplying together variables is a continuous function, that height varies smoothly as you move around the domain of the functions. You move around on the xy plane. So what you get is this blue surface. So this is the surface whose height above any particular point in the base, in the xy plane, the domain plane, is given by the value of the function. So that's what's called the graph defined by the function, or really we should call it the surface defined by the function. Now we've got two sliders here which allow us to change the base point AB. What we can do is move one of them a fair bit down and move one of them a little bit down. So we're now looking at this base point AB, which is approximately 0.7 and minus 3. Okay, so you can see this base point here in this black dot there in the plane. So the coordinates of that black dot, it's more or less down at minus 3 here, and it's just a little bit up on the x-axis away from x equals 0, so 0.78 or whatever on the x-axis. And superimposed on the graph there, I'll zoom it up a little bit for you. Okay, the red one is quite distinct, but what you can actually see here are two cross-sectional curves. Okay, you can see this red curve, which is parallel to the x-axis, and it's a little bit indistinct. The colors don't come up that great on the screen, but there's a green curve running here, which is parallel to the y-axis. And these are the two cross-sectional curves across the surface, which intersect the surface, which both go through the base point AB. What you've got below here are those two cross-sectional curves plotted out just on their own, okay? So this is like taking a knife and slicing the surface parallel to the x-axis through the point AB, and you'd slice it along that red curve there, and that would be what the edge looks like, the cross-section looks like. And slicing the curve, slicing the surface parallel to the y-axis along through the base point AB. Okay, and you get this. Some of you at the front might be able to see it, or maybe at the back. This green cross-sectional curve. That'll be the slice of the curve where you slice the surface. And what we've done here is just displayed those cross-sectional curves across the surface. Okay. Now the computer code is also working out the partial derivatives. Okay. So f subscript x is the partial derivative of f with respect to x, and f subscript y is the partial derivative of f with respect to y, and it's evaluating them at the base point. And this allows us to see the graphical meaning, the graphical interpretation of what these partial derivatives are. These partial derivatives give you the gradients of the tangent lines to the corresponding cross-section of the surface. Okay? So this red one is the cross-section of the surface parallel to the x-axis. The x derivative is 2.8 approximately. When you evaluate it at this base point AB I defined using the sliders. And you see that the tangent to this curve here, this is the base point reproduced here, the tangent to the red cross-sectional curve, well, it is quite steeply rising at this point. Okay? So if you imagine the tangent curve here, it corresponds to that gradient of 2.8, a gradient of nearly 3, which is extremely steep. Yeah? For every one step forward, you're taking 3 steps up. Okay, so it's quite a steep rise there. Whereas the y derivative evaluated at that base point, the computer calculates it as approximately minus 0.5, minus 0.6 or whatever. And here's the base point where this cross-section was cut through the surface parallel to the y-axis. Indeed, yeah, you can see here, you've got the curve is decreasing at this point. So the tangent has got a negative gradient here, negative slope, pointing downwards. Okay, it's It's not quite pointing downwards at 45 degrees, but nearly so. If it was pointing downwards at 45 degrees, it would have a tangent of -1. It's not so steep there at that point, but it's near -0.66, so nearly -0.7. So encapsulated in that short little section there, that short little description in the notes, we can see being illustrated in this widget. Okay? What the partial derivatives mean graphically or geometrically in terms of the surface defined by the function is gradients of those curves, gradients of those cross-sectional curves through the surface. So I'll put the link to this demo sheet up here, and you'll be able to change the function, change the limits on the x and y variable, and interact with the thing here, change your base point and move the base point around and for different cross-sectional curves. Okay, so we've still got 8 minutes or 7 minutes on that, so we're going to just look at the first of the examples on the extra problem sheet. But just to say, for your tutorials this week, either with myself on, is it tomorrow morning? Maybe myself or Wednesday, or Stephen or Frank later on in the week, depending on who your tutor is. This first batch of exercises in exercises 1.1 would be the one to look at. Okay, and I've also so we've also got a bunch of extra practice problems for you to be working with here as well. So all these problems require you to apply this principle of partial differentiation to answer these various things. I'm trying to put in some interesting differential equations here. We're not solving these differential equations by any means here. We're simply verifying that they do have the solutions that they claim. So the first of these is Laplace's differential equation. Okay, so these are important in applied mathematics. So let's just have a look at how we might treat some of these. So the kind of things you need here are that principle of partial differentiation in bold, combined with everything you know about single variable calculus as well. Okay? So you got to take all that stuff you have from Maths Fundamentals last year, combine it with this new principle of partial differentiation in order to treat your multivariable functions. Okay? So if you have a look at this first problem, we've got this partial differential equation, d2 phi dx squared plus d2 phi dy squared equals 0. That's a much harder problem to generate the solutions just from the equation. That's not what I'm asking you to do here. I'm asking you to simply do is to verify that this function up here, this function phi of 2 variables, is indeed a solution of this equation. Okay? So we're going to verify that this function phi, which is e to the x sine of y, solves this ODE. Solves this PDE, partial differential equation. So what we need to do is work out both of these partial derivatives and just demonstrate that they satisfy the equation. Yeah. Well, they're both second order partial derivatives, so to get there, you first need to work out the first order partial derivatives. So the first order partial derivative, the derivative with respect to x of phi of xy, so we use the principle. What we see here is really just the exponential, e to the x. It's multiplied by sine y, but that won't trouble us because we're differentiating with respect to x. Sine of y acts merely as a constant. You just imagine it as the number 2 here, multiplied by e to the x. Just some constant multiplied by e to the x. So the derivative of that is, well, what's the derivative of the exponential function? E to the x, it's just e to the x. The derivative with respect to x. It's a special property the exponential function has, is It is its own derivative. So the x derivative looks nice and simple. It hasn't really changed at all. And indeed, if you just go and differentiate it again, well, if you differentiated it once with respect to x and nothing changed, do it again, you're still going to see, here we're doing d dx of e to the x sine of y. Okay, so you take the x derivative and you differentiate it again with respect to x. But again, that isn't going to change. So there's the first part of the PDE, d2 phi dx squared. For the second part, d2 phi dy squared, so we first go for the y derivative. So now you're differentiating this with respect to y. So just ignore the complication of the exponential. It's just some number times sine of y. The derivative of sine, we know to be cosine of y. And of course, you still have that same constant that was there multiplying the sine of y, that's still there multiplying the derivative of sine. Okay? So that's how you treat constants when you're differentiating a constant multiplied by sine of y. Okay, that's the first derivative with respect to y. The second derivative with respect to y, by definition, will be the first derivative of the first derivative. So d dy of e to the x cosine of y. Well, this time, again, this e to the x is going to survive here as a multiplier, where you're differentiating cosine of y. The derivative of cosine is, of course, minus sine. So you get minus e to the x sine of y as the second order y derivative. PDE says add these two together and get the value 0, and of course that's what happens. Okay? Take the second order x derivative, add it to the second order y derivative. They do indeed cancel out, and you do indeed get 0. So d2 phi dx squared plus d2 phi dy squared equals 0 as required. Okay, so you've got a whole bunch of extra problems there to be working with. You've got the first set of tutorial exercises, exercises 1.1 to deal with. So plenty of work to be getting on with.